Imagine stepping into a spacecraft where you don't float, you walk, your feet press firmly against the floor, your inner ear feels balanced, your muscles carry your weight just like they do on Earth, and for a moment, the stars outside the window seem less like a distant frontier and more like a new neighborhood. The most shocking part is this: the tech to create that experience might already exist, just not the way most people imagine. What if artificial gravity isn't about bending space-time, or inventing some sci-fi gravity generator, but something far simpler, something we've already built in the real world, and tested and proven? And if that's true, then why haven't we seen a single NASA, ESA, or SpaceX mission bring artificial gravity into spaceflight? The answer is stranger, more frustrating, and more exciting than you might think. Right now, as humanity prepares for deep space missions to Mars and beyond, scientists are racing to solve one of the biggest unsolved problems in space travel. The human body begins to fall apart in microgravity. Bones thin, muscles weaken, vision changes, the heart reshapes. Even the brain shifts within the skull. Long-duration astronauts on the ISS return to Earth biologically older in ways medicine still doesn't fully understand. And this isn't theoretical. NASA's twin study, published in Science, found measurable changes in gene expression after long-term exposure to microgravity. So the obvious question is, why we haven't built a spacecraft with artificial gravity when the concept has existed for more than half a century? Before we answer that, here's a quick reminder to join us on this journey. If exploring the future of space technology excites you, stay close, subscribe, like, and turn on notifications so you never miss the next leap in human innovation. The core truth about artificial gravity is surprisingly simple. We already know how to create it: spin. That's it. According to basic physics, if an object rotates fast enough, anything inside it feels an outward force that mimics gravity. It's called centripetal acceleration, and it's the same reason you feel pulled outward on a spinning carnival ride. This is not speculation. Engineers use rotational gravity in training systems, amusement rides, and laboratory experiments. Space science papers published by NASA, ESA, and private researchers confirm the math is straightforward. Rotate a spacecraft ring or habitat at the right radius and speed, and you get gravity-like force. But that simplicity leads directly to the biggest engineering barrier. To make artificial gravity feel comfortable, you need size, you need radius, you need space, because small spinning structures create something astronauts absolutely hate: nausea. The problem is called the Coriolis effect. When your inner ear senses rotation but your brain interprets your motion differently, the result is disorientation. Imagine turning your head in a spinning room and immediately feeling like the floor tilts sideways. NASA experiments in the 1960s and again in 2000s on rotating rooms showed that humans can adapt to rotation up to about 4 revolutions per minute. Beyond that, the discomfort becomes overwhelming for most people. At 2 RPM, many people feel fine. That sounds good. Until NASA engineers do the math. To produce Earth gravity at 2 RPM, the structure has to be enormous, hundreds of feet across, something no rocket has ever launched into orbit in a single piece. So yes, in theory, artificial gravity is easy, but in practice, it demands megastructures we haven't built in space yet. This is where the dream gets complicated. Every space agency agrees artificial gravity is the most important long-term health technology for human exploration. But they also agree that building a spinning habitat in orbit is one of the hardest engineering challenges humanity has ever considered. It's not the rotation that's difficult, it's the construction. The International Space Station at 109 meters long took 13 years of assembly, dozens of missions, billions of dollars, and a multinational workforce. A functional rotating habitat would likely need to be 2 to 3 times larger, and it would have to not just exist in space but spin evenly, maintain structural balance, and withstand constant stress loads. Yet despite the obstacles, the idea refuses to die because the alternative, sending astronauts to Mars with no gravity for 6 months, is almost medically impossible. Researchers at the Translational Research Institute for Space Health have published reports warning that deep space crews face irreversible consequences without gravity exposure. That's why interest in artificial gravity has exploded over the last decade. And in 2025, for the first time, multiple real projects are making progress. One of the most ambitious concepts today is the rotating space station designs proposed by private aerospace groups like Orbital Assembly. Their plan involves 2 major structures, a small-scale rotating test habitat and a much larger ring-shaped space station. These designs promise partial gravity for long-term visitors. While none of these stations exist yet, the idea is no longer conceptual art. Engineers have tested structural segments, control systems, and connection mechanisms designed to withstand rotation. NASA has also funded academic studies exploring modular rotating habitats that could be assembled in orbit using existing launch vehicles, rather than waiting for next-generation super-heavy rockets. But there's another approach. Instead of building massive spinning rings, what if a spacecraft simply spun two modules connected by a long tether? This idea, first explored by rocket pioneer Konstantin Tsiolkovsky over a century ago, keeps returning because it solves the size problem. A tether system creates artificial gravity by spinning two masses around a central point. It's elegant, it's efficient, it requires far less material than constructing a huge rigid ring. And in 2023, the MIT Space Exploration Initiative conducted small-scale experiments to study tether behavior in microgravity environments. The results showed that deployment and stabilization are not only possible but surprisingly stable. The challenge is controlling the rotation safely. If anything breaks or destabilizes, the spinning masses can become dangerous. But researchers are optimistic, and with modern materials, tethers may become one of the first practical paths toward artificial gravity. Right now you might be wondering why no one has simply launched a rotating module to the ISS to test the theory. NASA has considered it multiple times with proposals such as Nautilus X, which included a small centrifuge meant to give astronauts partial gravity for exercise or sleep. But funding, schedule shifts, and changing priorities pushed the idea aside. Instead, researchers have run dozens of Earth-based rotating room studies to simulate partial gravity, including work published in the Journal of Vestibular Research, showing that humans can adapt to rotation more easily than previously believed. Still, until something spins in orbit, we won't know the full biological impact. The future of space tech is unfolding faster than anyone expected, and you can stay ahead of every breakthrough. Subscribe, like, and turn on notifications so you stay connected to the technologies shaping our future. The real turning point may come from a surprising direction: space tourism. Private companies want hotel-style habitats with artificial gravity because tourists aren't trained astronauts. They don't want nausea, bone loss, or floating food trays. They want comfort. This pressure is accelerating investment in rotating station concepts that NASA never prioritized. For example, Orbital Assembly's planned Voyager station includes rotating habitation decks with simulated gravity levels. While timelines are often optimistic in the private sector, the mere fact that these projects have architectural plans, engineering partners, and early-stage construction tests means artificial gravity is closer than ever. Another major factor pushing the technology forward is the rise of heavy-lift rockets. SpaceX's Starship, if it reaches fully operational status, could launch massive habitat modules or rotating segments that simply weren't feasible with earlier rockets. A 2024 paper from the University of Colorado Boulder outlined how modular centrifuge habitats could be sent up in segments and assembled robotically, using autonomous drones, technology NASA has already tested for on-orbit construction. If you can build a rotating module in orbit without human assembly, the cost and risk drop dramatically. Starship might be the enabling infrastructure that turns artificial gravity from concept to reality in less than a decade. But even if we can build it, another question remains: should it simulate full Earth gravity, or something less? Partial gravity, like the 0.38 g on Mars or 0.116 g on the Moon, may be sufficient to maintain health while requiring far less rotational speed. If true, a Mars-bound spacecraft might only need to generate 1/3 gravity, which dramatically reduces engineering complexity. In other words, partial gravity might be the key that unlocks practical artificial gravity without requiring megastructures. However, even partial gravity systems introduce new engineering problems. A rotating spacecraft experiences constant stress at its joints, bearings must run flawlessly for years, vibrations must be controlled, spin rate must remain stable even as the spacecraft changes mass, for example, when using propellant. Then there's the challenge of docking. You can't easily dock a non-rotating spacecraft to a rotating one. This means you need to stop the spin, dock, then re-accelerate the rotation. That requires energy, precision, and precise control systems. NASA studies from the 1970s all the way through updated 2020 technical papers warn that stopping and restarting a massive habitat's rotation repeatedly could fatigue the structure over time. And yet, these obstacles don't make artificial gravity impossible, they just make it difficult. The difference matters. Many futuristic technologies require scientific breakthroughs we haven't reached. Artificial gravity is not one of them. The physics works, the biology supports it, the engineering path is visible. The real challenge is simply building big structures in space, something humanity is only just beginning to master. In some ways, artificial gravity is the perfect symbol of our moment in space exploration. The science is ready, the need is urgent, and the missing piece is the infrastructure to build at scale in orbit. Picture the moment when the first astronaut wakes up in a spinning habitat after a long sleep, stretches, stands, and feels their weight settle naturally beneath them. It will be the first time a human has ever lived in gravity that wasn't born from a planet or moon. It will feel familiar, grounding, even comforting, and yet it will mark a turning point in our species' story. The moment we learn to bring gravity with us wherever we go. That moment will change everything about long-term space travel. It will protect the bodies and minds of future explorers. It will open the door to multi-year missions into deep space. It will make life beyond Earth feel not just survivable, but livable. And the most hopeful part of all is that the technology isn't centuries away. It's on the horizon now, being shaped by breakthroughs in materials, robotics, construction, and private sector ambition. Stay tuned as we uncover the technologies that will reshape how humanity lives, travels, and thrives beyond Earth. Subscribe, like, and turn on notifications so you never miss what's coming next. This is Tech Mythos.